Hi and welcome everyone again. In this video, I want to go over characteristic equation, and what we're going to talk about is homogeneous linear equations with constant coefficient. So first about homogeneous, we know that the right side should be equal to 0. Constant coefficient, that means these numbers are constant. So, and we're going to concentrate on second order linear constant coefficient differential equation, and of course homogeneous. Ay double prime plus b times y prime plus cy equals to 0. Now if you watch the last videos, solving those equations are pretty straightforward, but in this video I want to go over kind of the proof of the solutions, and for you to know where those solutions come from. Now we learned that the general form, or when we have an equation like this, then the solution can be written as y equals to e to the power of mx, or sometimes you see y equals to e to the power of rx. We can take the first derivative, which is m e to the power of mx, and the second derivative, which is m squared e to the power of mx, and substitute into this equation. So we get am squared e to the power of mx plus bm times e to the power of mx and plus c times e to the power of mx. We can factor out e to the power of mx. We're left with am squared plus bm plus c equals to 0. We know this cannot be equal to 0, so we have to take that quantity and put it equal to 0, or I put that also, sometimes it's presented with either exactly the same thing. Now this is a quadratic equation. It's also called the characteristic or auxiliary equation. To solve a quadratic equation, we know we can factor if it's factorable, or we can complete the square or use the quadratic formula. If you use the quadratic formula, the solutions are written as negative b plus or plus square root of b squared minus 4ac over 2a, or negative b minus square root of b squared minus 4ac over 2a. The radicand here is called the discriminant. And let's see what happens. If the discriminant is positive, you know you're going to have two real roots, distinct real roots. If the discriminant is 0, this disappears. It's 0, you're left with negative b over 2a. That's a repeated root. So m1 and m2 are real, but they are equal. If that's negative, then you know you're going to get a negative number under the radical, and that's complex. So you have the +1 and the -1. So what you get is conjugate complex numbers. So one solution is a plus pi, and the conjugate of a plus pi, we know it's a minus pi. Then we're going to talk about the solution fast. Then I'll kind of tell you where they come from. Case 1, if we have distinct real roots. Case 2, you're going to have repeated roots, and case 3 are complex roots. If you have real roots, the solution is e to the power of mx. So you have two solutions. y1 is e to the power of m1x, and y2 is e to the power of m2x. And if you use the superposition principle, please watch the last videos. Then we know if these two are linearly independent, and they are, the way you check that, you can use the Wronskian. Please watch the video on that. Then by the superposition principle, we know that the general solution will be any linear combination of these two solutions. So the general solution can be written as c1 e to the power of mx plus c2 e to the power of mx. If you have repeated roots, case 2, then we know the numbers are the same, and you can call that m. So for sure that solution is easy to see, is e to the power of m1x. However, this is second order, so you have to have a second solution, and the second solution is x e to the power of m2x, but m1 and m2 are the same. So again, the general solution, after checking that they're linearly independent, the Wronskian, and you can write that as C1 e to the power of mx plus C2x e to the power of mx. That x you might ask where this is coming from. I will explain that at the end of this lecture. Please be patient. If you have a conjugate complex roots, so you know one root is alpha plus I beta and the other one is the conjugate alpha minus I beta. So one solution is y1 is e to the power of I plus alpha plus bix, and the other one is going to be e to the power of alpha minus beta x. And again, being linearly independent, you can write the general solution like that, but you don't want to have complex numbers in the solution. So somehow we have to move from complex to real ones, and that solution, this is the same thing as e to the power of alpha x, c1 sine beta x plus c2 cosine beta x. Now, I want to show you how we get from here to here. So let's go over the proof of that. To prove that, first you're going to use the Euler's identity. Euler's identity says e to the power of I theta equals to cosine theta plus I sine theta. And of course, if you put pi instead of pi, you get cosine pi plus I times sine pi. Sine pi is 0 and cosine pi is 1, and you get that equation, which is called the most beautiful equation in the world. Now, how do we get that? You need to refer to calculus 2. The power series for e to the x is sum n starting from 0x to the power of n over n factorial. So now if we come here, instead of x, we substitute I theta, then e to the power of I theta will be sum, the same thing, I theta to the power of n over n factorial. We expand that, and we start from 0, so you get I to the power of 0 theta to the power of 0 factorial. Remember, this is 1, any number to the power of 0 is 1, and 0 factorial is 1, so that's just 1. Then you get some odd exponents and some even exponents. So refreshing your memories of I squared is -1, I cubed is I squared times I is -1 times I is negative I to the 4th power is I squared times I squared, -1 times -1 is 1, and I to the 5th power is -1 times -1 times I, which is I. So 4 possible answers, -1, -I, 1, and I. And if I has an even exponent, either it's going to be -1 or 1. If it has an odd exponent, it's going to be either -I or I. Now, if we separate the even exponents with the odd exponents, we know odd exponents, they're all going to have this I. So that's what we're left with. Now, but what are those? Again, from calculus 2, the power series of cosine theta is sum -1 to the power of n theta to the power of 2n. These are even numbers over 2n factorial. That's exactly that. And we have that -1 to the power of n because it alternates. We have plus, minus, and so on. Sine theta can be written as, again, n starting from 1 now to infinity, -1 to the power of n minus 1, theta to the power of 2n minus 1 over 2n minus 1 factorial, and these are odd numbers. So it's exactly this one if you expand it. Therefore, e to the power of I theta can be written as cosine theta plus I times sine theta. And it's good to know sine is an odd function. Sine -x is negative sine x, and cosine -x is just cosine x because cosine is even. Now, before we get to the next part and then see how we get that solution, there is a little theorem I want to go over, and it's right here. And please remember this because I'm going to go up and use this. We have this equation y prime plus p of x, y double prime plus p of x times y plus q of x times y equals to 0, and I call that number 1. P of x and q of x are real valued functions, so they can even be constants. If ux plus I times bx is a complex solution, then both u of x and v of x are individually solutions of the differential equation. If you take the second derivative and first derivative of u of x and substitute, you're going to get 0 equals to 0 and same as v of x. There's a nice proof of that. Let me go over that. So we know this is the solution. So if we substitute, this is y double prime, and that's y prime, and this is y. So if we substitute those by u of x plus I times v of x, u of x plus I times v of x, and q of x times u of x plus I times v of x. Now the second derivative, again, if it's sum, you can separate them. You can say u double prime of x plus I times v double prime of x, and plus, same as here, you can separate those and then distribute the p, so you get p of x times u prime of x plus I times p of x u prime of x, and here you just distribute q of x and you get that. So now what we can do, we know that here also we have imaginary parts and real parts. If we separate them, the real parts are right here. So you get u double prime of x plus p of x, u prime of x plus q of x, v of x, and the imaginary part are those, which is that one, and we have that one and that one. So we can factor out I and write it. That should be equal to 0. Now, when you have a complex number, when you put it equal to 0, you can't say equals to negative bi. You have to take the real part, put it equal to 0, and the imaginary part and put it equal to 0. And if you take that, put it equal to 0, and this one and put it equal to 0, guess what we get? These equations are exactly like that, number 1. So u double prime, u prime of x times q of x times u of x equals to 0. So u is a solution for that, which is going to be the solution for number 1, and v is a solution for this one, which is going to be also a solution for that one. So, and I put here 1 and 2 look like number 1. So therefore they're both solutions. So let's go up and continue the rest of the proof. After that is pretty straightforward. So coming back here, when we know we can write y as c1 e to the power of alpha plus beta ix and c2 e to the power of alpha minus beta x. So now what can we do here? We can, by using rules of exponent, let me refresh your memory so we can separate those. So it's just e to the alpha x e to the beta xi, and this one is e to the alpha x e to the negative beta xi. We can factor out e to the power of alpha x, and that's what you're left with. Now we can continue here, or let's do something else here. When we can factor out e to the power of alpha x. So, and now what we know that e to the power of beta x can be written as cosine beta x plus I times sine beta x, and that's from Euler's. And if it's negative, and since we said sine is an odd function, then we can write that as cosine beta x plus I times sine minus I times sine beta x. Now here we can say c1 plus c2, factor that out, and we are left with cosine beta x, and here we can factor out an I, and a c1 minus c2, we are left with sine beta x. Now that's a complex solution. If it's a complex solution, guess what we said? We said if we have a complex solution for that equation, then the real part itself is a solution, and the imaginary part, sine beta x, also is a solution separately. And again, here C1 plus C2, you can just use C1 because it's a constant and that's a constant. So that's why the solution, if we come back, this is going to be one solution is e to the alpha x cosine beta x, and the other one is e to the alpha x sine beta x. There's another way to prove that. You can just say, take one case, C1 equals to C2 equals to 1, or C1 or C1 equals to 1, C2 equals to -1. But if you use that, that's going to prove it. Now, this is the fundamental set. What we need to show, if these two are linearly independent, so then the linear combination of these two, any linear combination of these two, will be solution of the differential equation. To show that they are linearly independent, again, we use the Wronskian. You take e to the power of alpha x cosine beta x, the derivative of that, take that function and you take the derivative and you find the determinant, and we know this is not equal to 0. One reason is e to the power of 2x is it can never be equal to 0. So therefore, these two are linearly independent, and this is the set of the fundamental solution. This is the fundamental solution set, actually. And you can, any linear combination of those can be the solution of the equation. Here, there's some examples. Again, this is just second degree, so it's, you can, all you have to do is take that, put equal to 0, the quadratic equation, and solve it. Now, if the degree is higher than 2, so same way, you write the equation and you have to find the possible zeros, and you can use synthetic division, which I did in my last videos. And if you find that, then you can get one of the zeros and the other one is right here. So if you solve this, you get a pair of conjugate complex. So how do you write the solution? And we can call this the homogeneous solution. So it's C1 e to the power of x over 3 plus e to the power of -x, because that's alpha, C2 cosine square root of the x, and plus C3 sine square root of 3x. And you see, even if the degree is 3, the solution is written the same way. Now, there are examples solved in the other videos, but let's go over the repeated rules. And here I want to show you how we can get x e to the power of m2x. So repeated rules and reduction of order. This is our differential equation, and we know we get the characteristic equations. Here I used R just to be familiar with M and R both ways. And we know that this is going to be equal to 0. So we get one solution, and we write that's like R minus 3 squared, and or we get that solution. Now let's first look at an example how we can get the second solution. So if we had to solve this, we know this is R minus 3 squared, so R equals to 3. So we know, we saw that y1 is e to the power of 3x, and even if we write y equals to c to the power of 3x, it's going to work. So any multiple of that solution will be a solution. Now instead of c, let's take v of x, and we can find y prime, which is use the product rule, v prime of x times e to the power of 3x and 3 e to the power of 3x times v of x. That's the product rule. Then we can find y double prime. Again, you have to take the derivative of that. which is the product rule again, and you have to take the derivative of that, which is the product rule again. If you do that, then you get v prime of x e to the power of 3x, 3 to the power of 3x, v prime of x. The derivative of that is the derivative of the first one, 9e to the power of 3x times the second one, v of x, and v prime of x times 3e to the power of 3x. Now, if we write, and that's what you get. And what I did, instead of v of x, I just used v's, so it's easier to see. So at the end, we get that. So, and if we go back, and if you simplify that, this is your final answer for y double prime of x. Now we have this equation from the beginning. If we substitute, so y double prime, we found it. It's right here. And 6 times y prime, we found that too. It's right here, plus 9 times e to the power of 3x times v. Now, then we can simplify all this, and guess what? This is an equation, and they all have e to the power of 3x. So if you multiply every single term by e to the power of 3x, we are going to be left with that. And if we simplify, these cancel each other at the end, and let's see, we have 9v plus 9v minus 18v, they cancel. We're left with v double prime equals to 0. Now what we can do is find v prime. We just take the integral of both sides, and the integral of 0, we know it's a constant. Then if you want to find v, then we can write v as c of x, c times x plus c2. And all I'm doing is taking the integral of both sides. Now if we write the solution again of that, we can get y equals to c of x plus c2 times e to the power of x. And guess what that's gonna give us, because we found v here. So if we go back and write the solution for that, so we can write that as c1x plus c2x e to the power of 3x, which is that. And guess what? This is our y1, and that's our y2. So that's how we get that second solution. Now you can do the same thing, but generalization means here the last one I took an example, but then what was the solution is negative b over 2ax. And if you take that equation and put equal to 0, you know the answer is going to be negative b over 2a. And you can do the exact same steps by finding the first derivative and the second derivative and substituting. And this is like pure algebra, substituting and canceling. And if you do that, so you do get, this is our y double prime, and if you substitute, this is our y prime, and this is our y. And then what you can do, again, simply divide everything by b over 2ax, and just make it simple, use v's, and you are going to be left with that. They all cancel the same way we did the example. And if you do that, you're going to be left at the end. If you simplify everything, please try that on your own and look at the notes. And if you do that, you get v double prime equals to 0. Same way, you can find, take the derivative, you can find v prime, which is c1, and v is going to be c1x plus c2x. So y equals to v of x times that, but v of x you substitute, that's what you get. And guess what? If you write the solution, you get this, and it's exactly the same answer. So that works always when you have a repeated rule. I think that's good enough for this lecture. Please watch it a couple of times and try those on your own. It's just algebra. It's not very hard, but simplifying it, it's long algebra. Thank you for watching, and I'll see you in my next video. Have a good one.